Hello, I'm just going to go through a couple of examples of the balancing equations that we've seen in the balancing equations worksheet. So you should be able to find this worksheet in the folder labeled balancing equations. What I'm going to do is pick a few of these on the left hand side here, and then I'll just do one of these questions in the middle to show you again how you convert the word equations into chemical equations themselves. So let's have a look. So in this, I'm going to be using what I call the roster method. So that is basically counting up the atoms that you have on each side and then following a process to balance them. Some tips that I have for this method: leave elements to last all the time. That's because you can change the numbers in front of them without changing all the other elements. So always leave those to the end if you can. Start by balancing the biggest disparity, so wherever there are a lot more atoms on one side than the other, you want to find the biggest difference and start by balancing that. Usually that will then pull a few of the others through to balance as well, which is great. Finally, if you get really stuck, try and find some common multiples. So if you've got something that is 3 and 7, then you're going to have to try and get 21 atoms in total by getting 7 3s and 3 7s together. So it's a bit of a trick, and we're going to see an example of that one later on. Great, so let's get our pen going, because this always goes so well. And let's start with our roster method. So first of all, I'm going to draw a line down where the arrow is and start thinking about these two equations, as having two sides. So I start by writing out all the elements that I have. So I've got C, H and O in this equation there, and again I write it exactly the same if I can on the other side of the page as well. And then I start counting. How many carbons have I got? It's CH4, so that's just one carbon. How many carbons have I got on the right hand side? Just the one. CO2, that's it. There's no number after the C, so we're done. How many hydrogens have I got? I've got 4 hydrogens because it's CH4. Okay. On this side, I only have 2 hydrogen atoms there. And finally, oxygen. I've got 2 on this side. On this side, I have 2 in the carbon dioxide and 1 in the hydrogen, in the water. I almost said dihydrogen monoxide. In the water itself, so that is 1. Okay, so I'm going to leave elements to the end if I've got any. Have I got any elements? Yeah, oxygen's an element. It's just on its own. There's only one elemental symbol in there, so I'm going to leave that one to last. So what's the biggest disparity? It's the hydrogens, isn't it? I've got 4 on one side and 2 on the other. So I have to make it such that there are 4 hydrogens on this side. So that means that I need 2 water molecules. If I have 2 water molecules, I've got 2 lots of H2, which gives me the 4 and the O. And then I suggest that you cross everything out and count up again. Now, again, you'll get to the point where you don't need to cross everything out, but I'm just going to do that as we start off, and then we'll see if later on I do it. So I've got carbon with just the 1, hydrogen, I've got 2 lots of H2, that's 4, as I would expect. And now I've got 2 O's and, I've got O2 there, so that's 2 oxygens, and I've got 2 H2O's, so that's another 2, to give me a total of 4. Carbon is currently balanced, so now, because I left oxygen to the end and it's an element, I know that that's the only thing I have to do. So I have to make it so that there are 4 oxygens on the left-hand side, and because my oxygens come in pairs, O2s, I need 2 of them. Again, I would cross everything out, but seeing as we can already see that we've only changed the oxygen here, then I've got 1 carbon, 4 hydrogens, and 4 oxygens. This equation is balanced then. No atoms are appearing or disappearing, they're just being rearranged from one side to the other. Okay, great, so that's question 2. Let's move on. Okay, this one's a bit more tricky, so again, I'm going to get my line down there. I'm going to write out the elements. So we got K, potassium, we got O, oxygen, we got H, and we've got P, and that's it. So potassium, oxygen, hydrogen, and phosphorus. Let's count each one up. So on this side, potassium, just the 1 potassium. On this side, I've got 3 potassiums. Over here, oxygen, I've got 1 there, And 4 over there in the H3PO4 gives me 5. So 1 from the KOH there. And oxygen's on this side. I've got 4 there, KPO4, and 1 from the hydrogen. So that's also 5 oxygens. Hydrogen atoms, I've got 1 in KOH and 3 in the H3PO4, gives me 4 in total. And on this side, I've only got 2 in the H2O. Phosphorus atoms, I've got 1 on this side and I've got 1 on the other. Okay, so I haven't got any elements in this one. There's no equation, there's no formula, sorry, that has only one elemental symbol in it. So that's a pain. We're going to have to deal with changing one thing is going to change everything. But as I mentioned, balancing the biggest disparity first tends to solve a lot of problems. So which one's the biggest biggest disparity? It's the potassium, isn't it? I've got 3 potassiums on the right hand side and only 1 on the left. So in order to make this correct, I'm going to put a 3 here. And then I'm going to cross everything out and update it all. Again, do not use the method of going, okay, I've got 3 KOHs, so now I've added 2 KOHs. I've added 2, I've had Ks, 2 Os, and 2 Hs. It leads to disaster. It's way better just to recount them all. So now, how many Ks have I got? I've got 3 Ks. How many O's have I got? I've got 3 KOHs, so I've got 3 there and 4 over there is a total of 7. Okie dokie. I have hydrogens. How many? 3 there and 3 there is 6. Alright then. And phosphorus, I've still got just the 1 there. Okay, great. So now I go and look again at my biggest disparity. It's my hydrogen, isn't it? I've got 6 on the left-hand side and only 2 on the right. So let's make it so that I've got 6 hydrogens on this side. I'm going to put a 3 here in front of the H2Os. Now again, obviously I don't have to cross out all of these, but I'm going to just because it's good practice right at the start to do it. And then eventually you can stop once you realise that sometimes this is pointless. So how many Ks have I got? 3. I'm counting across the whole row here. How many oxygens have I got? Well, I've got 4 there. And I've got 3 H2Os, so that's 7 now. How many hydrogens have I got? I've just got 3 lots of H2 is 6. How many phosphoruses have I got? Just the 1. Oh, right, look, it just balanced then. That's it. So I've got 3 potassiums on both sides. I've got 7 oxygens on both sides, 6 hydrogens on both sides, and 1 phosphorus on each side. So that's it. Now, you can, if you want, put 1 in here, but it's a bit pointless, isn't it? So usually I just leave it completely empty. If it says H3PO4, that means 1 of those. Let's keep going because we're on a bit of a roll now. This is question 11. So what elements have we got now? We've got Na, we've got C and N. So I'm gonna keep those separate. Sometimes with ions, it is useful to think about keeping them together, but let's not for now. Let's keep C and N separate. I've got copper and I've got oxygen. Again, I'm going to try and write them in the same order on this side. Sodium, carbon, nitrogen, copper and oxygen. And we're just going to count them up. So sodium atoms, I've just got the 1 there in the NaCN. Carbon atoms, I've got 1 in the NaCN and 1 in the copper carbonate there. So that's 2. Nitrogens, just the 1. Now be careful, don't count that N because that's an Na. We just need N on its own there without any lowercase letters after it. So we just got the 1 N there. Copper, we just got the 1. Oxygen, we got 3, CaCO3. Now, before I was going straight across the row, so whichever one feels more comfortable to you, I tried it a different way this time. Sodium atoms, I've got 2 of those, Na2, and that's it. Carbon atoms, oh, I've got 1 there. And then I've got a Cn, all in brackets 2, so that means 2 copies of the Cn ion, I guess in this case. So that means I've got 2 of those. How many nitrogen atoms? Again, I've got Cn2, so that's another 2 of those. Coppers, I've only got the 1 copper. Whoops. Okay. I've learnt the hard way that I can't undo that, so sorry, that's going to be there. And the oxygens, I've got 3 on this side because I've got NaCO3. Okay, So I have not got any elements, annoyingly, so I'm just going to have to balance everything. And everything is okay except for the Na and the N at the moment. So let's balance Na because it's the first one there. I need to have 2 sodium atoms. So have I got that right? Ah, yes, yeah. So I've got 2 sodium atoms there. Again, I'm crossing everything out, but of course you wouldn't usually cross everything out, but I am just so that we count them all again. Sodium, I've got 2 of them. Carbon, I've now got 3 of them. Okay. Nitrogen, I've got 2 lots of Cn, so now I've got 2 of them. Copper, I've still got just the 1 in the CuCO3. And oxygens, yeah, I've still got 3 CuCO3. Okay, so now how are we looking? Oh, our carbons aren't balanced anymore. That's annoying. So what are we going to do? Let's look at it. We got our sodiums balanced. We got our carbons balanced. Not balanced. Oh, so here's why we cross everything out and we check it again. Look, I miscounted them. We've got 1 carbon there and a Cn2. I missed this one over here. So that's carbon 3 there, not 2. Brilliant. Okay, so this happens to all of us. Or if you get really stuck, just make sure your roster is correct. And it wasn't in this case. That is meant to be a 3. Okay, great. So it's balanced. Lovely. That was much easier than I thought it was going to be. So that's great. Let's look at a hard one now. I know this is a hard one because vanadium is in the 5+ oxidation state, which is an odd number. So let's do it. We got our line, we got vanadium, we got oxygen, we got hydrogen, and we got chlorine. Over here we've got vanadium, oxygen, hydrogen, chlorine. So how many vanadium atoms have I got on the left hand side? I've got 2. I'm going to go over the row again just because we might as well see a few different ways. I've got 1 over there. How many oxygens have I got on this side? Oh, 5. I've got 5 of them. On this side, I've got 1 there and 1 there for 2 oxygens. Hydrogens, I've just got the 1 in the HCl. Hydrogens on this side, I've got 2 in the H2O. And how many chlorines have I got? Just the 1. And on this side, I've got 3. Okay, so that being the case, what we're going to do? Well, we could balance vanadium, but the biggest difference here, we got no elements again. So I think the biggest difference is the chlorine. They're 2 different, or the oxygen. You can think about it that way as well. Now, why would I shy away from the oxygen at this point? Because oxygen appears in 2 different substances on the right-hand side. It's here and here. And that means that balancing it is going to be a bit of a pain. I might leave that one till later and just see if it resolves itself, because quite often it does. So yes, oxygen and chlorine are both the same, but oxygen's a little bit more complicated, so I'm going to start with the chlorine. Okay, so I need 3 chlorines on the left-hand side there. That's relatively easy. I'm going to have 3 HCl's. Again, I'm crossing everything out. That is, to some degree, to avoid what happened in the last question there, because I would have double-checked it every single time, wouldn't I? So now I've got vanadium. I've got 2 of those still. Oxygens, I've still got 5. That's all correct. Hydrogens, I've now got 3, because that was the whole point. And chlorines, I've got 3 there. Okay. Great. So now I'm going to have to think about my oxygens. Now, because I've got chlorine balanced, I'm probably not going to change the VOCl3, because if I change that, then I'm going to mess everything else up. So I'm going to assume that my balancing is going to happen over here, I think. Okay, so let's just double check. We've got O5 there. Yep. Oh, now we got our vanadiums. They're not balanced, so let's balance those. That's going to be interesting. So now we're into a part of an iterative process where we're going to have to go forwards and backwards. So I'm going to balance my vanadiums because I'm noticing that I can't leave that VOCl3 on its own anyway, because I need to balance the vanadium too. So I'm going to have to go forwards and backwards on this one. I got 2 lots of that to balance my vanadium atoms. Again, I'm crossing everything out to try and avoid what happened in the last one. So now let's check. Yeah, I've got 2 vanadiums. How many oxygens have I got? 2 in that. So 2 there and 1 there is 3 in total. How many hydrogens have I got? Still only 2 there. And finally, how many chlorines have I got? I've 6 now. Ugh, I just balanced those as well. So I've got 6 chlorines. So now I'm going to have to go back and balance again. So I'm going to go back to my chlorines and I'm going to say, okay, that's not a 6. That's not a 3, sorry. It's a 6. So now, if it's a 6, again, let's update all of our roster just to check. Vanadiums, still 2. Oxygens, still 5. Hydrogens, I now have 6. Chlorines, I now have 6. Okay, so my chlorines are balanced. My hydrogens and oxygens are not balanced, but everything else is. Great, because I've got water left, and water contains hydrogen and oxygen. If I've done this right, this is just going to balance itself, which is brilliant. So, let's do the hydrogens, again, because oxygen appears in both of them. So I've got hydrogen, 6 hydrogens on that side, 2 on the other. Means that I need 3 water molecules to provide the 6 hydrogens that I need. Again, crossing this out to double check all my answers. Vanadium, yeah, I got 2 of them. Oxygens, now I've got 2 there and 3 there is 5 in total. Hydrogens, I've got 3 lots of H2 is 6. Chlorine, I've got 2 lots of Cl3 is 6. Whew, finally, we're balanced. So you might find that you have to go through a process where you balance one and that knocks another one out, and eventually you get to there. Again, don't worry about shying away from the very, very complicated ones. You might find that they resolve themselves at the end. So there, that was the oxygen. The oxygen was difficult because it starts in one molecule and ends up in 2 different molecules, so balancing was going to be tricky. Finally, let's look at the second page here where it gives us word equations that we have to transfer into written equations. Now, sulfuric acid, you will eventually learn, but that's not until lecture 7. So for now, I've told you that the chemical formula for sulfuric acid is H2SO4. That is the sulfate ion that you've already learnt with 2 hydrogens on it. So we got that. And now lead 4 hydroxide. Lead 4, that's the Roman numerals. Just in case you're not aware of what the Roman numerals are, we'll just pop them over here on the right. Yes, 1. So 1, 2, 3, 4, 5, 6, 7. That's probably as far as we're ever going to go, but we'll just do 8, 9, 10 just for fun. So the Roman numerals are I for the first one, I for the second, I for the third. The 5th is V, so I'm just going to draw that like that. The 4 is a 1 before the V, hence IV for 4. For 6, it's 1 after the V, so VI. 7 is 2 after the V. VII. 8 is 3 after the V. 10 is X. And so 9 is 1 before the X. So sorry about a bit of Roman numerals there, but it's well worth having a look at them to make sure that they make sense to you. So we got lead 4 hydroxide. That being the case, that means that we've got lead, which is Pb. You would look at the periodic table to figure that one out. 4 plus. That's what the IV, the 4, means there in the Roman numerals. It means it's in the 4 plus state. If we have a quick look at the periodic table, lead is right at the bottom of group 4. It's in the 1, 2, 3, 4, 5, 6 P2 position, proton number 82. The fact that it's in group 4 explains why it ends up being 4 plus ions. What about the hydroxide? The hydroxide is one that we also saw in the common list of ions. That is OH minus. Sorry, that's a minus charge there up at the top. So I need 4 OHs for every 1 lead to cancel out the charge overall. And so that will take us to the equation of Pb. And then we're going to say, oh, I've got 4 OHs. 4, like that. Okay, it goes to make lead sulfate. So now the lead is still in the Pb4 plus state. But I've also got a sulfate. Now that is one of our common ions. It's SO4, 2 minus. So if I've got a 4 plus and 2 minus ions, then the formula must be that I need 2 sulfates for every lead to cancel out the charge. So I'm going to write PbSO4 2. And water. Water is H2O. I expect you to remember that one if you don't mind. Great, so now let's use our roster method. Can we see anything so far that's going to be troubling to us? So we have H, we have S, we have O, and we have Pb, lead. So I'm going to do the same order over here, H, S, O, Pb. Doesn't matter what order these are in, as long as they're the same on either side. H, I've got 2 hydrogens there, and 4 over here, because I've got OH 4 times, giving me a total of 6. Over on this side, how many hydrogens? Only the 2 in H2O, so 2 for those. Sulfur. Just the 1 sulfur on this side. But on this side, I can see that I've got 2 sulfurs, because I've got SO4 2. Oxygens, ooh, quite a lot on this side. We've got 4 in the H2SO4, and then 4 lots of OH means that I've got 4 there for a total of 8. On this side, I've got SO4 twice, so I've got 2 lots of 4 is 8, plus this 1 over here for the water is 9. And finally the leads, I've got 1 on this side and I've got 1 on that side. Okay, so what is balanced and what isn't balanced? Oh look, hydrogen isn't balanced, but the sulfur nearly is. Okay, So what would I do first? I think what I'm going to do is I'm going to balance the sulfur first, even though it isn't the largest disparity. The reason I'm doing that is because the sulfur is part of a compound that has quite a lot of elements in it. And so again, if I try balancing that, I think it might balance all the other ones. So I'm going to start with my sulfur. And to make 2 sulfurs, I'm going to put a 2 in front of that. Now, this one's tricky. If you went any way, you'll find that it would be fine. If you used any method, you'd end up going forwards and backwards. My shortcut here is the sulfur, because I'm noticing that the SO4 is unchanged really. It just swaps partners, but it's still an SO4. And so I'm trying to imagine that as one whole unit, and I'm going to balance the SO4s on their own. So I'm going to update my roster. I'm going to update my whole roster again, just to avoid making mistakes. So hydrogen, I've now got 2 lots of H2 is 4, plus the 4 OHs there, gives me 8 in total. Sulfurs, I've got 2 from the 2 H2SO4s. Oxygen, I've now got 2 lots of 4 and 4 lots of 1, so that's 8 and another 4 is 12. And lead, I've still only got 1. Okay, so now I've got sulfur and lead all balanced. The oxygens aren't balanced and the hydrogens aren't balanced, but that suggests that what I'm going to do is mess with the water instead. Now I'm noticing that I haven't given myself very much space in front of the water, so I'm just going to erase that plus and then pop a new one in like that. Okay, so let's balance these hydrogens. I have 8 on the one side and 2 on the other side. So if I want 8 hydrogens now, on the right hand side, I'm going to have 4 water molecules, aren't I? 4 water molecules. So again, I'm going to update everything just to be sure that it's all balanced. So I've got 4 H2Os, gives me 8 H2Os there. 8 H's there. Sulfur, yeah, still 2 there in the brackets. 2 lots of SO4. Oxygens, okay, I've got 2 lots of 4 there is 8, plus 4 is 12, lovely. And just the 1 lead. Okay, brilliant, we're all balanced. 8 to 12, 1 on both sides, ba-boom, means that that is balanced. So I hope that's helped you having a look at some of those examples. Give the rest a go, and the answers are available also in the same folder. Okay, thanks very much.